Welcome students. Today I shall discuss about the topic of connectedness. Before going to the definition of connectedness, we first introduce the definition of a separation of X. Let X be a topological space. A separation of X is a pair U, V such that X can be expressed as disjoint union of two non-empty set U and V. Now we shall introduce the definition of connectedness. A topological space X tau is said to be connected if there does not exist any separation of X. That is, X cannot be expressed as disjoint union of two non-empty open set X. Naturally, connectedness is obviously a topological property because it depends on collection of open sets of X. Now we shall introduce our first theorem. The following conditions are equivalent for a topological space X. First one, X is connected. Next, the only subset of X that are both open and closed in X are the empty set and X itself. And finally, number 3, every continuous mapping f x to plus minus 1 is a constant function. Proof is 1 implies 2. That means we assume X is connected to prove that only subset of X that are both open and closed in X are the empty set and X itself. If possible, let there exist a non-empty proper subset A of X which is both open and closed. That means the property 2 is not happen. Then X can be expressed as capital A union X minus A. Capital A is non-empty and capital A is a proper subset. So X minus A is non-empty and X minus A also proper subset. Where A and X minus A both are open sets in X. Because A is a closed set, so X minus A is an open set. Which is a contradiction since X is a connected set. That implies first one is over. Next, for 2 implies 1. The only subset of X that are both open and closed in X are the empty set and X itself. Then prove that X is connected. If possible, let X be not connected space. So X can be expressed as disjoint union of two non-empty open set U and V. Since U is a open set, so its complement, that is X minus U, that is nothing but it is equal to V, is a closed set, as well as U is closed also. So V is a both closed and open set, and V not equal to phi and X, which is a contradiction. Hence the result. That means X is connected. Next one, 1 implies 3. That means let X is connected space and f is a mapping from X to plus minus 1 is a continuous function to show that f is a constant function. If possible, let f is not a constant function. That implies f is a onto function. Let capital A is equal to f inverse minus 1 and capital B is equal to f inverse 1. Minus 1 is a open set of the set plus minus 1, because with respect to subspace topology, minus 1 is a open set of the set plus minus 1. So f inverse minus 1 is a open set because f is a continuous function, so inverse image of open set f is also open. Similarly, from similar reason, 1 is also open set of plus minus 1 by subspace topology, so inverse image of f under the mapping f is also open. That implies B is open. So A or B both are open sets and both are non-empty, because f of A is goes to minus 1 and f of B is goes to 1 and f is onto. So capital X is equal to capital A union B. That means X can be expressed as disjoint union of two non-empty open subset of X. That implies X is disconnected, which is a contradiction. So every continuous mapping X to plus minus 1 is a constant function. And finally, 3 implies 1. let us assume X is not connected. Therefore, there exists two disjoint proper subset. Obviously, both of them are open sets A and B, call it A and B, such that X can be expressed as A union B. Now we define a mapping f x to plus minus 1 such that fx is equal to 1 if x belongs to capital A and fx equal to minus 1 if x belongs to capital B. Then obviously this mapping is a continuous mapping. Why it is continuous? Let G be a open set in plus minus 1. So f inverse G is equal to x if capital G contains minus 1 and 1 both, and it is equal to capital A if G contains 1 but not minus 1, and f inverse G is equal to B if G contains minus 1 but not 1, and finally f inverse G is equal to phi if G contains none of minus 1 and 1. Then the above four sets, capital X, capital A, capital B, phi, all are open sets in X. So f inverse G is a open set in X. Therefore f is a continuous function and which is also non-constant. This implies there exists a continuous function which is onto which is onto and from x to plus minus 1. This completes the proof. Our next example is the subset Q, that is settable rational number, and R minus Q, that means settable irrational number, in real number space with usual topology are disconnected. Solution is, since root 2 belongs to R minus Q, that means root 2 is a irrational number, then the set Q, that means settable rational number, can be expressed as disjoint union of two non-empty open set. That means left hand side set, that means my open interval minus infinity root 2 intersection Q union open interval root 2 comma plus infinity intersection Q. That means about root 2 we consider all rational number less than root 2 and we consider all rational number greater than root 2. Then Q can be expressed as disjoint union of two non-empty open sets over Q with respect to subspace topology. That implies Q is not connected. Similarly, since 0 belongs to Q, then R minus Q, that is settable irrational number, can be expressed as R minus Q is equal to open interval minus infinity to 0 intersection R minus Q union open interval 0 infinity intersection R minus Q. Both of them are non-empty and open, and 0 belongs to, because 0 belongs to Q, that means 0 does not belong to R minus Q. So every irrational number can be expressed as two part. One part is less than 0 and another part is greater than 0. That means R minus Q can be expressed as disjoint union of two non-empty open sets with respect to subspace topology or relative topology. So R minus Q is a disconnected set. Our next example is, let capital X be a set such that cardinality of x greater than or equal to 2 with discrete topology, so that x is not connected. Solution is, since x can be expressed as singleton x union capital X minus singleton x, so x can be expressed as disjoint union of two non-empty open set. Why is non-empty? Because discrete topology, in discrete topology every subset of x is open, so singleton x is open, and also capital X minus of singleton x is also subset of capital X, so it is also open. So both of them open and both of them non-empty. Why non-empty? Because cardinality of x is greater than or equal to 2. So first one contain only one element, that implies the next one or second one, x minus singleton x, is also contain at least one element. So both of them are open and both of them are non-empty, and x can be expressed as disjoint union of two non-empty open set. So x is not connected. Now we introduce a important theorem. The interval, that means all bounded interval, is always connected. Proof is, let us consider a function f closed interval ab to plus minus 1 be an onto continuous function. Then there exists x and y belongs to closed interval ab such that fx is equal to minus 1 and fy is equal to 1. Why it is possible? Because the function, we assume the function is onto, so there exists at least one point small x and a point y such that fx equal to minus 1 and fy is equal to 1. So it is possible. Then by intermediate value property, because the function is continuous, so using the intermediate value property or using the intermediate value theorem, there exists a real number z belongs to open interval a xy, assume x strictly less than y such that fz equal to 0. But which is a contradiction? Which is the contradiction, since 0 cannot belongs to the set plus minus 1. Hence, no such function exists and hence closed interval AB, that means closed bounded interval AB is a connected set. Our next example is, let capital A be a two connected sets in X. Then the set A intersection B and A union B may not be a connected set. Solution is, that means we assume two set. Let capital A is equal to order tuple x comma 0. That means x comma 0 belongs to R square such that x belongs to real number, and B is equal to all such xy such that x square plus y square is equal to A. X square plus y square equal to 1. First one, A is nothing but it is a x-axis and B is nothing but it is a circle with center at 0, 0 and radius is 1. Be two subset of R square, then A intersection B, it is equal to plus minus 1, and it is obviously with respect to subset topology disconnected, so intersection B is not a connected set. Next we assume capital A is equal to all such order table x comma 2 such that x belongs to a real number. That means it is nothing but it is equal to y equal to 2 line, and all such B such that x square plus y square is equal to 1. That means again a unit circle center at 0, 0. B two subset of R square, then A union B is a disjoint union of two non-empty open sets, so A union B is not connected. Now we introduce another theorem. Let AB be two connected subset of capital X such that A subset of B. Then obviously A intersection B is equal to B, so it is connected. And next one is, let capital A and B be two connected subset of X such that A intersection B not equal to 5. Then A union B is a connected set. And finally number 3, let A be a connected subset of X and let capital A subset of B and that is subset of A bar, then B is connected. That means if B is equal to A bar, then A bar is connected. So that implies if A is a connected set, so A bar is connected. Now an important question is that, is the result 1? That means AB be two connected subset of X such that A subset of B, then A intersection B is a connected set. That means is the result 1 of the above theorem is true for infinite sequence of connected nested sets. That is A1 subset of A2 subset of A3 and so on, where each of AN is connected, then intersection n equal to 1 to infinity AN is connected. Is it possible? Which follows from the following example. Given an example of a sequence AN of connected subset of R square such that AN plus 1 is a proper subset of AN for all n belongs to natural number, but that intersection n equal to 1 to infinity AN is not connected. Solution is, let us consider a set AN is equal to R square minus all such order tuple x comma all such order pair x comma 0 such that x belongs to minus n comma n for all n belongs to natural number. Then it is obvious that A1 is subset of A2 and it is obviously proper subset of A2 and obviously proper subset of A3 and so on. And the intersection is all such order pair xy belongs to R square such that y greater than 0 and all such order pair belongs to R square such that y less than 0. That means the intersection n equal to 1 to infinity n, the whole plane R square into two parts. One part is positive part of y and another is y is negative. So that means intersection n equal to 1 to infinity n can be expressed as disjoint union of two non-empty open sets. So intersection n equal to 1 to infinity n is not a connected set. Now we introduce another important theorem. Let X be a connected space and G X to Y be a continuous mapping, then Gx is connected. Proof is, if possible, let Gx is not connected. Then there exists a non-empty proper subset U subset of Gx which is both open and closed in Gx. Since Gx is a continuous function, so G inverse U is a Clopen set. Why it is Clopen? Because U is open, so U inverse G inverse U is open and U is also closed, so G inverse U also closed. So that is why G inverse U is a Clopen set in X, and G inverse U is not equal to phi and X, since phi is a proper subset of U and U is proper subset of Gx. This contradicts the hypothesis that X is connected. So Gx is always a connected set, provided small g is a continuous mapping. Our next example is, which of the following sets are connected subset of R square? Number 1, capital A is equal to all such order pair xy such that x square by a square plus y square by b square is equal to 1. That is nothing but is the equation of ellipse. Center at obviously 0, 0. Number 2 is B is equal to all such order pair such that xy is equal to 1. That means it is a rectangular hyperbola. Solution is, for 1, let us consider a continuous mapping f small f from closed boundary interval 0 to 2 pi to R square such that fx is equal to a cos theta comma b sin theta for all theta belongs to closed interval 0 comma 2 pi. It is nothing but it is a parametric equation of ellipse, and f is obviously continuous because sin theta and cos theta both functions are continuous, so f is obviously continuous. And we know that the closed interval 0 comma 2 pi is a connected set and f is a continuous mapping, and we know another important theorem, continuous image of a connected set is connected, so we get capital A is a connected set. For second one, let capital B is equal to order pair x comma 1 by x belongs to R square such that x strictly greater than 0 and union x comma 1 by x belongs to R square such that x strictly less than 0, which is a disjoint union of two non-empty open set in B with respect to subspace topology. Because B is nothing but it is an equation of rectangular hyperbola, so there are two parts. One part lies in first quadrant and another part lies in third quadrant. So B can be expressed as disjoint union of two non-empty open sets with respect to relative or subspace topology. So B is not connected set.